Jnanam paramam dhyayam. Knowledge is supreme.
Now, second one, we want to prove that for second one we may assume V is non-zero, because V is 0, then by we have made the convention so that they are equal, both are -1, and let us put S equal to S of M. See, what we want to prove, second inequality is, we want to prove that D of V is smaller or equal to S of V. This is what we want to prove. To prove this, we assume V is non-zero, because if V is 0, both are -1. So, now if you call S to be S of V, that means I have S elements A1 to AS in the maximal ideal of A, such that length of V by A1 to AS times V, this length is finite. That is the definition of S of V. Therefore, because the length is finite, the support of V by A1 to AS V, this consists of only singleton M, because if your moduli is finite length, then the support consists of the maximal ideal. And let us put this ideal to be Q, ideal generated by A1 to AS, and this actually let us put Q equal to this ideal plus annihilator of M, annihilator of V. This is contained in M, and now we claim that this Q is primary. Q is M primary. Okay, for that it is enough to prove that if enough to prove that if Q is contained in some prime ideal P, then this P must be maximal. That will prove it is M primary. So, suppose on the contrary that we are in such a situation, Q is contained in P and P is not the maximal ideal. Suppose on the contrary that Q is contained in P and contained in properly contained in M, then P is not in the support of V by A1 to ASV, that is at localization this module is 0. So, that is Vp is same as ideal generated by A1 to AS Vp, and again by Nakayama lemma Vp is 0. That means P is not in the support. That means P is not in the support of V, but support of V is V of the annihilator. P is not there means P does not contain annihilator. Annihilator of V is not contained in P. But this is a contradiction. Because we have assumed that Q is generated by the annihilator of V and along with A1 to AS. Okay, so we have proved Q is primary and dm therefore is dV therefore is degree of Hilbert-Samuel polynomial. I can use now this Q primary this. Now if you put A prime to be the residue class ring of A by the annihilator of V and M prime to be the ideal, the image of the ideal, the maximal ideal M in A prime, and Q prime to be the image of Q in A prime, then the Hilbert polynomials PQ prime V and PQV, they will not change because we have gone modulo the annihilators. So, the annihilator kills the module M, therefore, the P will not change and degree of, so D of V, which is by definition degree of PQV, which is degree because of this equality degree of PQ prime V, which is less equal to mu of Q prime, which is now Q prime, Q was generated by A1 to S along with annihilator of M, but we have gone mod annihilator, so that disappears and this mu of Q prime is less equal to S, which is S of V. So, we have proved the second inequality. So, a second inequality was D of V is smaller or equal to S of V. The third and last inequality now we want to prove is that S of V is smaller or equal to dimension of V. This is to prove. So, first of all note that the dimension of V is finite, because we have proved in inequality 1 that dimension of V is smaller or equal to the degree of the Hilbert-Samuel polynomial and the degree is integer. So, therefore, dimension is finite, and to prove this again we may assume V is non-zero. So, suppose if the dimension is 0, then if the dimension is 0, that means the chain has only one element in a support, because the supremum is 0. So, there is only one element in any chain in the support. So, that will mean that support of M support of V can only be the maximal ideal, because if it is not maximal ideal, you will have at least 2 elements in the chain in the support. So, dimension will be non-zero in that case. So, if dimension is 0, support of V will be exactly one element, namely the maximal ideal, and therefore, the length of the module V is finite then, because support of V consists only the maximal ideal, the length is finite. So, that will mean that, so that is S is 0 then, because I can simply take empty set, empty sequence A1 to S, and then mod that V mod that is V, and the length is finite. So, by definition of the Chevalier dimension, I can take S to be 0. So, in this case, so we proved if dimension is 0, then this is also 0, and then it proves this inequality for dimension V equal to 0. Now, assume the dimension is positive. Assume that dimension of V is positive, and choose and let P1 to PR be elements in the support such that dimension V is dimension of A by Pi for I equal to 1 to R. So, what I am saying is, we know that the dimension is finite. So, that means all chains of prime ideals in the support of V, they will have finite lengths, and in any maximal chain which gives the dimension, in that I choose the left end point, and that is called P1. For another chain there may be another one, so P2 and so on. So, I call P1 to PR all those prime ideals for which the dimension V is precisely the dimension of A by Pi. These are in the support of V, and they will be by automatically they will be the minimal primes in the associated primes of V, and therefore, they are finitely many. Okay. No, I just call that R. R is some number, right? See, there are finitely many of them, so I call that number to be R. Okay. So, because now we are assuming dimension is positive, none of these Pi's will be M. So, Pi is not M for all I equal to 1 to R, since dimension V we are assuming is positive. And now, look at their union P1 to PR and M. This M cannot be contained here in the union, because if M is contained in the union, then it will be contained in one of them, and then therefore, because M is maximal, it will be one of the Pi, but that is not the case. So, M is properly contained in P1 to PR. This is also called prime avoidance lemma. So, that means I can choose an element in the union which is not in M. So, choose, so there exists A in M which is in none of the primes, P1 to P1 union PR, and take V prime equal to V by AV, ideal generated by AV. And now note that the support of V prime will be contained in support of V, and none of the P1 to PR are in the support of V prime. because when I localize V prime at any one of them, this A is not in Pi, therefore, this will become 0. With this A will become a unit and therefore, this model will become 0. So, that implies this. Therefore, when I want to compute a dimension of V prime, we have to take the chains of the prime ideals in the support of V prime, but none of these guys are there. So, any chain will not contain this. So, therefore, this will be at most dimension V minus 1. And now, by induction, dimension S of V prime is smaller or equal to dimension of V prime, and obviously S of V is smaller or equal to S of V prime plus 1, because at most one element I will add to that, then you will get the number of generators for the Chevalier dimension of V will be at most one more than the Chevalier dimension of V prime, and this is less equal to dimension of V prime plus 1, but this is dimension of, this is less equal to dimension of V, shifting the earlier inequalities minus 1 to the other side. So, that proves the third inequality, and with that, therefore, it proves the theorem. So, now I will deduce few consequences. So, corollary 1, dimension of a module is finite. Remember our assumption, V is a finitely generated module over an Noetherian local ring, and we have proved that this dimension is same as the degree of the Hilbert-Samuel polynomials, and degree is always finite. So, therefore, this is finite. In particular, dimension of a local ring is finite. Dimension of a local ring is finite. Corollary 2, if Q is M primary, then the dimension of V is bounded by mu of V, mu of Q. Mu is the minimal number of generators for Q, which is by Nakama lemma, this is the dimension of the A by M vector space Q modulo M times Q. In particular, dimension of the ring, local ring, is less equal to mu of M, because M is M is M primary ideal, and mu of M is by definition or by Nakama lemma, it is dimension of the A by M vector space M by M square, and this number is also called embedding dimension of A, M dim A. That is the definition of embedding dimension of A. I will write it on the next page. Embedding dimension of the local ring is by definition mu of M, which is equal to by Nakama lemma dimension of the K vector space M by M square. So, dimension is bounded by the embedding dimension. If M is non-zero, V is non-zero, and if the dimension of V is, let us call it D, this is bigger or equal to 0 because V is non-zero. This means there exists, now I use the definition Chevalier dimension, there exist D elements A1 to AD in the maximal ideal M such that if I go modulo these D elements, length of V by A1 to AD times V, this is finite. So, such a system of elements A1 to AD, such a system A1 to AD is called a system of parameters. For the module V. So, number of elements in a system of parameters for a module, degree of the Hilbert-Samuel polynomial, and supremums of the chains of the prime ideals in the support V, they are all same numbers. That is what the content of the dimension theorem is. Okay, the next. This D is the dimension of D, right? So, okay, corollary 3. This is very important theorem in local algebra. Okay, if I have R elements in the maximal ideals A1 to AR, then and if I go modulo this A1 to AR in any module, that means if I consider a module V and consider a residue class module V by A1 to AR, this module, then the dimension of this is bigger equal to dimension of V minus this number R. So, proof. So, dimension can drop at most by R elements. Okay. Moreover, equality holds if and only if. So, equality here holds if and only if these elements A1 to AR, this system A1 to AR can be extended to a system of parameters for V, then only the equality will hold. Okay, so proof. So, let us put V prime equal to this quotient module or this residue class module. And D equal to dimension of V prime. We want to prove that dimension of V prime is dimension V minus R. Okay. If this D is dimension of V prime, that means by a definition of equality, Chevalier dimension of V prime will be D. That means there will be D elements in the maximal ideal. So, that if I go modulo V prime, those D elements, the length will be finite. So, this means there exist elements B1 to BD in maximal ideal M such that length of V prime modulo ideal generated by B1 to BD times V prime, this length is finite. But look, this module, this factor module, quotient module B1 to BD V prime, this is same as V modulo, because V prime is V modulo A1 to AR and along with this. So, this is V modulo A1 to AR along with B1 to BD. This length is finite, but then by definition of Chevalier dimension, that the dimension of this Chevalier dimension of this will be less equal to R plus D. So, that implies dimension of V, which is S of V, which is less equal to R plus D, but this is equal to R plus dimension of V prime. So, that proves this inequality. So, that proves dimension of V prime is bigger equal to, shift this R to the other side, dimension R minus R. Now, the moreover part, suppose the equality holds. If the equality holds, the equality means dimension of V equal to R plus D, where R and D as above, then this will mean that A1 to AR along with B1 to BD, this is a system of parameters for V, because dimension is R and this number of elements are also correct, and mod those number of elements dimension the length is finite. Therefore, by definition of system of parameters, A1 to R comma B1 to BD is a system of parameters. So, if equality holds, then this A1 to AR we have completed to a system of parameters. So, that proves the one implication. Conversely, if A1 to AR can be completed or can be extended to a system of parameters, let us call it A1 to AR comma C1 to CS in M, the system of parameters for V, then the length of V prime modulo C1 to CS V prime, this is finite, where V prime is V modulo A1 to AR, but this residue class module is same as, this is same as length of the inside the residue class module is V by A1 to AR C1 to CS V. This length is finite. Therefore, by definition of Chevalier definition, this proves that this S is at least D, because D was the dimension of V prime. This is the dimension of V prime. But then dimension of V will be bigger equal to R plus S, which is bigger equal to R plus D, which is bigger equal to dimension of V. So, all inequalities are equalities. In particular, we get dimension of V equal to R plus D, which is R plus dimension of V prime. So, that proves the equality. So, there are some more corollaries, but I will do that in the next time.